Hi everybody. In this video, we are going to prove that the square root of 2 is an irrational number. That means the square root of 2 cannot be written as a fraction of two integers. And the way that we're going to do that is by using a proof by contradiction. What that means is we're going to assume something, and then we're going to show that our assumption leads to an impossibility. It leads to something which cannot be true, and therefore our original assumption must have been false. So what we're going to do is we're going to assume that the square root of 2 is rational, and we'll see that since that leads to an impossibility, the conclusion is that the square root of 2 must not be rational. It must be irrational. So again, here's our assumption. Our assumption is that the square root of 2 is rational, meaning it can be expressed as p over q, where p and q are integers. And I'm adding this extra phrase here, with no common factors. So let me explain that a little bit. Let's say in class one day I said, okay, I am going to give everyone in class 5 homework passes. So this is something which I am doing generally to everyone. Okay, in general, it applies to everybody, no matter what you scored on the last test or what time you got to class. This is something which is general, which applies to everybody. Everybody gets these homework passes. Then I say, oh, okay, you know what? I changed my mind. I'm only going to give the homework passes to students who breathe oxygen. Well, at first people might get upset. Hey, I thought you were going to give it to everybody. And then they realize, oh, wait a minute, but everybody does breathe oxygen, so everybody is still included in that statement. So basically what I can say that I'm giving homework passes only to the students. I can add that phrase only to the students who breathe oxygen without any loss of generality, which means that no students get left out even when I add that little phrase. Now, I can add this phrase with no common factors, and I can do that without any loss of generality, because all rational numbers can be written with no common factors. So, for example, if I had, let's say, 0.8, I could write that as 80 over 100, but then I could find a common factor between 80 and 100, which is 10, and I could rewrite this as 8 over 10, but then I could find another common factor between 8 and 10, which is 2, and I could rewrite this again as 4 over 5, and I can just keep doing that. No matter what the integers in my fraction are, I can just keep doing that until I get it in reduced form, where 4 and 5 don't share any common factors. Okay, and since that applies to all rational numbers, it means that I can add this little phrase over here without any loss of generality. Okay, so that's our assumption. So once again, we're assuming that the square root of 2 is rational, which means that it can be expressed as a fraction p over q, where p and q are integers with no common factors. And what we're going to see is by making that assumption, it's going to lead us to some impossibility, something that can't be true, and therefore this assumption that the square root of 2 is rational must be false. Okay, so right now, though, we're assuming that it is true, which means we can write that the square root of 2 is equal to some integers p over q. We may not know what p and q are, but if we're assuming that the square root of 2 is a rational number, then there must be some integers, one for the numerator and one for the denominator, where this will be true. Okay? Now what we're going to do is here's the next step in the proof, we're going to square both sides. So remember, if two sides of an equation are equal to each other, then if I do the same thing to both sides of the equation, then the result must still be a true statement. In other words, if this was true, we're going to show that it's not eventually, but if this was true, then it must also be true that this squared is equal to this squared. Now, the square root of 2 squared would just be 2. Okay, so for example, if you don't understand why that is, then let's look at another example. What about the square root of 81? Well, the square root of 81 is 9, right? Because 9 times 9 is 81. If I take this and I multiply it with itself, so I square it, then it's like I'm doing 9 times 9, which is 81. Okay, so if I have some number under a square root sign, and then I square that, then I just get the number that was under the square root sign as my result. Okay? So if I square both sides here, then on the left side, this and this cancel, and we have just 2. And then on the right side, we have p over q to the second power, which is like p to the second power over q to the second power. Okay? The next thing that we're going to do is we're going to multiply both sides of this equation by q squared. We see that we have a q squared over here. I'm going to multiply this side by q squared, and then I'll multiply the other side by q squared. So these things are going to cancel, and my result, you know what, I'm going to keep it in blue. My result will be p squared equals q squared times 2, which I'll just write this way, 2q squared. I just changed the order here because usually the coefficient is written in front. So 2q squared is equal to p squared. All right, now I have this equation over here, and what I'm going to do is I'm going to sort of act like a detective. So you might have been wondering why I have this guy with a magnifying glass over here, because we're going to be doing a little bit of detective work in this proof. So based on this equation, we can figure out a few things that must be true about p and q, and we're going to use that information to prove that this must be false, that the square root of 2 cannot be rational, so it must be irrational. All right, so what do I know here? I know that p squared is equal to 2 times q squared. Again, I don't know what p is, and I don't know what q is, but this is telling me that if there are two numbers, p and q, such that p over q is equal to the square root of 2, then p squared must be equal to 2 times q squared. That's what I've figured out so far. And since p squared is equal to 2 times q squared, that tells me that p squared must be an even number. Now, how do I know that? If 2 times some number is equal to some other number, then this number over here must be an even number. For example, what if I'm just going to pick a number, 7. If I multiply 7 by 2, then I'll get 14, right? 14 is an even number, which just means it's divisible by 2. Okay, what if I picked another number, I don't know, what about 24? If I do 24 times 2, then I'll get 48. 48 is another even number. Of course, because I took some number and I multiplied it by 2. All being an even number, all that means is that it's divisible by 2. So of course, if I take a number and multiply it by 2 to get this one, then this one must be an even number. It must be divisible by 2. So the first thing which I guess do I kind of look like this guy? I don't have a mustache, right? Or a magnifying glass. Or a giant eye, for that matter. Oh, wait, no, that's the magnifying glass doing that. Anyway, so the first clue that I've uncovered here is that p squared must be even, because it's equal to some number multiplied by 2. Okay? Now, can I figure anything else out? You're probably guessing that I can, because I have these other 4 boxes here. Well, yes, I can figure something else out. If I know now that p squared is even, that actually tells me something about p itself. It tells me that p itself must also be even. How do I know that? Because if I were to take an odd number and square it, for example, 3, if I do 3 squared, which means 3 times 3, I get 9. Let's think of another odd number. If I do 5 squared, which means 5 times 5, I get 25. All right, if I do 11 squared, that's another odd number. 11 squared is 121. So notice what's happening here. I'm taking an odd number and I'm squaring it, and I always get an odd number as a result. 9, 25, 121, those are all odd. So anytime I take an odd number and I square it, I get another odd number. What if I take an even number and I square it? So for example, 4 squared, that's equal to 4 times 4, which is 16. Okay? 8 squared, that's equal to 8, that means 8 times 8, which is 64. 16 and 64 are both even numbers. So if I take an even number and I square it, then I get an even number as a result. So if p squared is even, that tells me that p itself must also be even. Right? P is the number that I'm squaring to get p squared. So if p squared is even, then the original number that I had, p, must also be even, because if it was odd, then I would have gotten an odd number as a result. Then I would have said p squared is odd. But since p squared is even, then the original p must also have been even. Okay? So I just used some detective work and I uncovered something else. Now, what else can I uncover here? I know that p is even. Can I use that to figure anything else out? Well, actually, I can. Knowing that p is even, I can figure out that... what's the next thing that I'm figuring out here? Oh, yeah. Since I know that p is even, the next thing that I'm going to figure out is that p squared must be divisible by 4. So, for instance, I have some numbers that I can use over here already. 4 is an even number. 4 squared is 16. 16 is divisible by 4, which just means that I can divide 16 by 4 and get a whole number. So 16 divided by 4 is 4. 8 is an even number. 8 squared is 64. 64 is divisible by 4. Okay, 64 divided by 4 is 16. But it works with any even number. So 6 squared is equal to 36. Okay, 36 divided by 4 is 9. 9 is another whole number. If I did 10, 10 squared is 100. 100 is also divisible by 4. 100 divided by 4 is 25. So anytime I take an even number and square it, I get as a result a number which is divisible by 4. So the next thing that we're going to uncover here is that p squared must be divisible by 4 because p is an even number, so therefore its square must be divisible by 4. Okay, so now I know that p squared is a number which is divisible by 4, and that's equal to 2 times q squared. Now again, I don't know what p is, and I don't know what q is, but I know that p squared is an even number, I know that p is even, I know that p squared must be divisible by 4, and now I can go back to this other side of the equation and think to myself, well, if this is a number which is divisible by 4, and this is equal to 2 times q squared, and q squared is just some other number, q squared must be an even number, because 2, there must be 2 factors of 2 over here, okay? If p squared is something which is divisible by 4, then on the left side, I must have 2 factors of 2. So for example, all right, let's say that, you know what, let me use that number again, 36. All right, if I were to do the prime factorization of 36, then I could do 9 times 4, and over here I could do, all right, 3 times 3 is 9, and 2 times 2 is 4. So anytime that I take a number which is divisible by 4, then I would get at least 2 factors of 2. It could be more. So for example, if I were to do 72 and take the prime factorization of 72, then that would be, I get 9 times 8. Okay, and then again, this would be 3 times 3, and this would be 4 times 2, and then this would be 2 times 2. So over here, I have 3 factors of 2. But anytime I take a number which is divisible by 4, then it must have at least 2 factors of 2 in the prime factorization. So let me go back to this number 36, and let me write it in a way which is similar to what I have over here, where I have 2 times some number. So I know that 36 is equal to 2 times 18. But I also know that 36 is a number which is divisible by 4, and therefore it must have in its prime factorization at least 2 factors of 2. And since I see one of the factors of 2 over here, and I only see one over here, that means that the other factor of 2 must be in this number. Okay, right? Because 8, and obviously that's true, 18 is 9 times 2, right? So the logic here is that if we have some number which is divisible by 4 on this side, and then on the other side we're writing that number as 2 times something, then the other factor of 2, the one other than this one, must be hidden somewhere in this number, which means that this number must be an even number. And indeed, 18 is an even number. Okay? So, because if something has a factor of 2, then by definition it's an even number. All right, so that means that since we know that p squared is a number which is divisible by 4, and we're writing it as 2 times something, it means that that something must have the other factor of 2 in it, and therefore it must be an even number. So we just learned that q squared must be even. Okay? Now, since q squared, we just learned, is an even number, that means by the same reasoning that we did back over here when we said p squared is even and therefore p must also be even, because only an even times an even gives us an even. If it were odd, an odd times an odd would give us an odd. So by that exact same reasoning, if I know that q squared is even, then q itself must also be even. Now I've uncovered all of the boxes, and you might be thinking, well, that seems a little bit anticlimactic. I thought by the time we uncovered the boxes, we would have the proof that square root of 2 is irrational, right? And you might be thinking to yourself, well, I don't see that here. So okay, so q squared must be even, p must be, so what? So how does that prove what we're saying over here? What we're going to do is we're going to erase everything that we've done except our original assumption. This is all we need to focus on right now. Our original assumption, which was that the square root of 2 can be expressed as p over q, where p and q are integers with no common factors. Except we just learned that if we write it this way, and we use a lot of logical reasoning, then we can figure out that p must be even, and q must be even. But wait a minute, if that's true, if p is even and q is even, then that means both of these numbers have a factor of 2. That's what it means to be an even number, is that you're divisible by 2, or you have a factor of 2. Okay, but they were not supposed to have any common factors. And therefore, we've reached a contradiction. Our original assumption logically leads to a conclusion which goes against itself, and therefore the original assumption must be invalid. The square root of 2 cannot be a rational number. It must be irrational. That's it. Have a great day.